thanks. That's a very generous introduction. Thank you for the invitation. And of course, I'm sorry, as everybody else, that we can't meet in person. So let me see if I can, yeah. Okay. Okay, so what I'm going to talk about today is most recent work which concerns PRISM, the probabilistic model checker that was developed in my group. It is an extension which is focused on model checking for stochastic games, and especially concurrent stochastic games and non-zero sum properties, equilibria-based properties. And this work also connects to verification for neural networks. So I'm trying to shift in that direction, and it actually connects to probabilistic verification for neural networks. I will try to time myself. I think it'll be quite hard, I think, with this, but so if, I don't know, if you can just wave at me if I'm taking too long, please. I can see Diego and Frank here. So, okay, thank you. So let's get started. So just to set the scene, I wanted to say that I think now we've got software and AI everywhere. And it's installed, you know, in all the devices around us. It's in autonomous cars, for example. And the user's expectation is normally to have predictability and also have high integrity. But this is in presence of what is often happening: component failure, environmental uncertainty, communication delays, etc., etc. Now, safety, security, reliability, robustness, they all have probabilistic formulations. And in particular, if we consider something like an airbag, then there is the property, safety property for an airbag would be that the airbag failing to deploy within 0.02 seconds, the probability of that happening is very small. It's, say, less than 0.001. Now, this is why I have, with my group, developed probabilistic model checking, and in particular, the PRISM probabilistic model checker. Now, PRISM can do automatic verification, but also strategy synthesis, and it can do it for temporal logic properties. So the idea is that in order to invoke PRISM, you need to give it a model, probabilistic model of the system. I'm showing you here the Google car as an example, but in fact, okay, you know, the airbag controller sitting in that car, or perhaps some other controllers, these are all probabilistic models that can be described in some sense in the language of PRISM, the modeling language of PRISM. And now, of course, for a car, the property that you would like to ensure is that my car never crashes. But in a stochastic world, that's not possible. So what we need to do is we need to talk about probability of these unwelcome events being small. And in fact, that's what this probabilistic property states there. P stands for the probability. The probability of F is the usual CTL operator. So the probability that in future within time t, my car crashes is less than 0.01. It's small. Now for this, if you feed a model and the property into PRISM, you get an answer, which is yes, this is satisfied or not. You can ask PRISM to return the probability and plot the results for different values of the parameters, but you can also return a strategy. And over the years, in fact, since 2000, around 2000, 2001, I have been working on the tool, which is called PRISM, and it is now a mature area of industrial relevance. There are new model checkers. There is a tool competition that has been deployed in many, many application areas, actually finding and correcting flaws in real-world systems. But the question I'm asking now, for the scenario that I showed you right at the beginning, what is the correct modeling abstraction? Now, so far, we have worked with models such as Markov chains and also with models with decisions, for example, Markov decision processes. That's all supported by PRISM. But what we have now is a very complex scenario where we have a mixture of human and artificial agents. They may have distinct goals. They want to optimize, for different properties, and they are autonomous, autonomous cars. They may need to compete for resources, but they may also want to collaborate. And of course, there is complicated context. Now, in these scenarios, we know economists tell us what we should consider is a game-theoretic view, and that shift is behind the extension of PRISM that I'm going to talk about. What we want to do is we want to account for these uncontrollable events and distinguish them from controllable events and synthesize strategies for different agents with respect to their different objectives and goals. So why games? Well, I'm going to use games, the examples, the standard examples here of different variants of games, which can be turn-based, concurrent. We can have game playing with human and artificial agents. We can talk about zero-sum properties or non-zero-sum, etc. Individual versus social games. So all these aspects are covered, and I'm using games as abstractions for the type of behavior that is going to be more effective because it will enable negotiation between virtual agents, strategic game playing, but also incentivization. So incentivize the correct behaviors. Now, they are relevant for a multitude of autonomous and AI scenarios. Distributed coordination, for example, there are protocols. The Aloha protocol is a game-based protocol, and even more recently, they started coming into autonomous driving. Just to give you one example here is hierarchical game-theoretic planning, where they use game-theoretic planning for long-horizon strategic game playing for cars to enable the negotiations and executing the maneuvers that are very difficult for autonomous cars to do. Merging into traffic is, in fact, very difficult. There are also Stuckelberg games being introduced in these settings. So that's just an example of the shift. But of course, even within the KR community, in the information systems community, games have had a long tradition, and strategic game playing and multi-agent systems are very prominent. So this lecture is going to focus on stochastic multiplayer games, and I will start with the simpler turn-based games, but the focus is really on the newest extension, which is for concurrent stochastic games and equilibria-based properties for these, which allow agents to have distinct goals rather than just play against each other in a zero-sum fashion. And I will say a little bit about what model checking involves and give you the link to the tool and also a summary of challenges and future directions. Okay, so what is a stochastic multiplayer game? Well, a stochastic game, obviously, it has to involve stochasticity, and that stochasticity comes from quantifying the probability of failures, perhaps from noisy sensors, perhaps intentional randomization in distributed coordination. But it will also involve multiple players, and these players will be non-deterministic because they will have a choice between moves they will have decision points, and these decisions can depend on history. Now, within this PRISM-games extension of PRISM, we started with turn-based games and more recently developed a concurrent variant and equilibria-based model checking. These are all for complete information games. Partial information has not been handled yet. But from the point of view of applications, there are numerous applications already, both within PRISM-games and outside. I mean, autonomous traffic, risk-averse versus risk-taking, selfish versus unselfish agents in distributed coordination, modeling system, and the system playing against adversarial environment, insecurity, defender, attacker. So there are multiple applications. Okay, so a stochastic multiplayer game formally is a tuple where I have n players and I have finitely many states. Now, for a game to be turn-based, I assume that this set of states is partitioned among the players. So in this game here, I have 3 players, the yellow, blue, and green, and the states are partitioned amongst those players. Now each player has actions. Actions are actually probability distributions. They have probabilistic outcomes. And I can also label the states with atomic propositions. Here you only see one atomic proposition, the check, the tick in the final state. Just think about it, that's a jackpot. So this is just a turn-based game. I will introduce concurrent games later. Now for games, since we have n players, each player will have an associated strategy, and strategy is basically a mapping from a finite history to finite history ending in a state belonging to that player to a distribution over actions. So in general, strategies are randomized, but a special case of this for direct distributions is, of course, the deterministic pure strategy. And we can talk about memoryless and finite memory variants, etc. If I take a tuple of strategies, one for each player, that is known as a strategy profile. And in a standard way, I can consider the paths unfolding the behavior of the system. I can put a probability measure over this. I can then have a random variable over the computations of the game. I can compute expectations over this. So in fact, in addition to just having labeling with atomic propositions and probabilities, I can also label the game with rewards, for example, elapsed time, energy consumption, net profit, etc. So what I then need to do, I have a model, a turn-based stochastic game, but I also need a logic. Now for that logic, I look to CTL. Now CTL is a basic branching time logic, but we consider it the coalition operator, which we take from ATL, alternating temporal logic. C is a coalition, is a set of players in these angle brackets. And we also add the probabilistic operator from the logic PCTL, probabilistic CTL, and R is a reward operator, essentially computing expectations, also from PRISM. So to start with, we just focus on zero-sum properties for turn-based games. And an example of an rPATL, reward probabilistic alternating temporal logic, that we have formulated is, okay, players 1 and 3 playing in a coalition, they have a strategy to ensure that the probability of an error occurring within 10 steps is less than 0.01, regardless of the strategies of other players. So I have n players. Of these, I select 1 and 3, they form the coalition, and the remaining players are in the opposing coalition. So this is a zero-sum game. Win for one corresponds to a loss for the other coalition. But also you can get a hint that I can reduce the verification to just considering two-player games. Okay, so formally for the syntax of my rPATL, I take CTL, but let's here just focus on the P operator and R operator, which are always combined with the coalitions. So the P operator, apologies for background noise. Okay, so for the P operator, what the semantics is saying, this is a state property. In that state S, this coalition CP bow tie Q, the bow tie stands for a comparison operator, and Q is a probability value, and psi is an LTL path formula. And the meaning of that is that there exist strategies for players in coalition C, such that for all strategies of the other players, the probability of path formula psi being true from state S meets the probability band. So for example, could be less than 0.01. And the reward operator is analogous, except that we are not talking about the probability of the path formula, but we are talking about an expectation for a random variable which is associated to the role, which will be specified by a reward structure. So that's the syntax. And just to have a look at this example, well, so this is a simple turn-based game. And let's consider the first property. So does the yellow player have a strategy to win the jackpot with probability at least a quarter? And the answer is yes, this is true in the initial state. But the yellow player does not have a strategy that will win with probability 1/3, and that is because the blue and the yellow player can play adversarially and can prevent him from getting to the jackpot. But if the yellow player plays in a coalition with the blue player, or also similarly with the green player, then they can both win the jackpot, and of course then they would have to share the proceeds. So that's the idea of the game. And what is the underlying problem that we are studying? Well, there is actually the verification problem, and also its dual, which is the strategy synthesis problem. The verification problem takes a game as a model and a formula, rPATL formula, rPATL property phi, which is in CTL style always a state formula, which may involve path formulas, psi as parameters. The question is, does the game satisfy phi? And what we do in this case is, because we only have coalition properties, we reduce the game, which is a n-player game in general, to a two-player game where player 1 is the coalition, player 2 are the remaining players, and we answer the question, does there exist a strategy for player 1, which is the coalition, such that for all strategies of the other coalition, the probability value meets the probability band. And the synthesis problem is dual. So for the synthesis problem, what we are looking for is we are actually looking for a witness. So we are trying to find if it exists a coalition strategy such that the coalition wins no matter what the other player, the players in the other coalition do. So this reduces to computing optimal values in winning strategies, because that's just zero sum for now, in two-player games. And complexity is NP intersect co-NP for the fragment that I showed you. Now what we do is we typically employ value iteration. So the complexity is not necessarily reflected in the complexity of the tool implementation, because we just compute it as the limit and we stopped when convergence has reached satisfactory values. Now both players get optimal strategies, memoryless strategies, etc. And we can extract the strategies in the same way. So for probabilistic reachability, now in fact this, if you are familiar with Markov decision processes, which are also known as 1.5 players, the computation here is analogous to Markov decision processes, except that in this case we have both the maximizing and the minimizing action, but we take them in states belonging only to one player, because we have assumed for turn-based games a partitioning of the states amongst the players. So one player maximizes, the other player minimizes. Okay. And with this, what we have done is we have analyzed an example, which was a real protocol, energy management protocol, and the protocol was analyzed using simulation. It was actually deployed in Kent for a group of houses as a kind of mini grid application where energy would come from a variety of sources. Now, what we actually discovered through the game-based model is that in the original protocol design, they assumed that all clients will behave properly. And in fact, there will be no selfish agents. Assumed that all clients are unselfish. Now with a Markov decision process model, you cannot identify this, but by introducing a game-based model, we very quickly discovered that if you allow the clients to cheat, then that exposes a weakness in the protocol, which we could also fix and verify. Okay, now, but in that case, what I was talking about is, well, turn-based games where I have finitely many states, I have finitely many agents, but each state is controlled by only one agent. So from that point of view, this is something that's kind of very similar to Markov decision processes. But that is not appropriate for many modeling scenarios. In autonomous traffic, what we have is we have actions and agents, taking decisions concurrently. So we need concurrent stochastic games. Now for concurrent stochastic games, I have finitely many states, finitely many agents. Agents also take decisions, so they are non-deterministic. They have several actions. But in each state of the game, agents independently take their choice, and the move corresponds to the vector of the actions, which would then take me to the next state. Now for this, I can also, in a very similar way to before, I can talk about strategy profiles, I can talk about the different type of strategies, history-dependent, randomized, memoryless, etc. And I can introduce the probability measure and expectation in a standard way as done for probabilistic model checking. So if I take this very simple example of a concurrent game, there is no stochasticity here. Rock, paper, scissors. So rock, paper, scissors is really a kind of an archetypal concurrent game. I have two players and they repeatedly draw between rock, paper, and scissors. So when you come into this state, the players independently choose, and then for that selected pair of actions move to the corresponding states. And as you can see here, rock, player, scissors is a draw, but player one wins if it chooses, rock, paper, scissors. Of course, rock, and the other one chooses scissors. So how do we represent such games? Well, it is well known, and here we draw from game theory literature, that this kind of concurrent game can be represented as a matrix game. This is a zero sum, so I can talk about a matrix game, and this is actually an example of a one-shot, one-step game. So for each state, if I want to consider an iterated game for each state, I have to be able to solve the matrix game, and I need to be able to iterate it over the computations. But of course, there are also standard ways, and there's the minimax theorem, which allows me to come up with an LP solution, which for concurrent and concurrent stochastic games in general will allow me to compute the optimal value, which in this case will maximize the value subject to the standard equations. So if I know how to solve my matrix games, if I also know how to do value iteration, which I know from the previous work, I can combine the two and obtain a method to do model checking for zero-sum properties for concurrent stochastic games. Now, the optimal strategy here, I'm sure a lot of you would know what to do. Okay, so what we can do in this case is we can just consider the same logic for zero-sum properties. We just make the model more general. Instead of turn-based games, we use concurrent games, but we have the same logic, so we also group players into coalitions, okay? And therefore, for the rock, paper, scissors game, I can talk about player one can ensure it eventually wins a round of the game with probability 1. Or, okay, the maximum probability with which player 2 can ensure it wins before player 1. So it's, imagine that I label not win 1 and win 1. That's the obvious atomic proposition labeling. But I can, so there is a typo here, this utility should be there. So this is an example of a reward property where I can talk about the maximum expected utility that player 1 can ensure over k rounds, okay? And the utility here can be 1, 0, or negative. So the logic, as I've mentioned, is the same, but of course the model checking is much more involved because I now need to compute solve a much more difficult problem. So in fact, the complexity is p-space. Although we use value iteration, so with value iteration we have an approximation. And it involves also solving the matrix game, for which we use SMT, so we solve LP, but we employ SMT solvers in order to compute these properties. Okay, but so far so good, but I have concurrent stochastic games, but I only have zero-sum properties. Now for multiplayer games, we want to consider properties where the players have distinct objectives, and therefore the games are not in general zero-sum. But well, in this case, I think for the, but I will come back to that in a minute when I introduce equilibria. First of all, I'm showing you an example of the difference that using a concurrent stochastic game versus a turn-based stochastic game can exhibit certain types of behaviors that were not seen before, and in fact actually can show advantages of certain types of cooperation, but also the fact that the market in a concurrent game, because the players independently make their choices. Okay, they cannot see. I will take 5 more minutes if you don't mind. Okay, so yes, so the players make choices independently, so they do not see the choice made by the other player. Now, in a turn-based game, of course, a player makes a move and then the other player responds, and that is a more complex situation. So this is an example of a future market investor game, and I'm showing you the difference that you observe for the same property, but using a concurrent stochastic game model versus a turn-based stochastic game model. Okay, and just to finish off, well, what we also want to do is to consider distinct objectives for each player and not necessarily restrict the logic to zero-sum goals. For this, we need to extend the logic, not just the model checking, we also need to extend the logic. And what we take as the basis is the well-known Nash equilibria, well, in fact, more precisely, subgame perfect epsilon Nash equilibria, because there are still open problems in this domain. And in fact, within the set of Nash equilibria, we look for Nash equilibria which are either social welfare optimal. Social welfare optimal means that they maximize the sum of the objectives, the sum of the payoffs, maximize the sum of the payoffs. You could have a lot of equilibria, but you only select the one that maximizes the sum of the payoffs. And similarly, social cost, that's dually rather, social cost Nash equilibria, which dually minimize the sum. Now, to enable Nash equilibria computation, I'm showing you an example for just 2 coalitional variant. I introduce a new type of property, so I specify a pair of coalitions. I also have the max or min, depending on whether I'm looking for SWNE or the social cost equilibrium, and I introduce properties. Okay, theta is a parameter, is a new property which can either express the sum of probabilities or the sum of rewards. Now, the semantics for this new extension is that this property is satisfied if there exist strategies for all players that form a social welfare Nash equilibrium between coalitions and under which the sum of the 2 objectives meets the probability bound. So meets the probability bounds either above some probability value or depending on the comparison operator. Now, I'm showing you here a true coalitional variant, but in fact, this has already been extended to M coalitional properties. And to show you an example for how this can be used, since I started with autonomous traffic, imagine an automated parking scenario where you are in a parking lot and you have, in this case, 3 cars and traffic is restricted only to the horizontal lanes. Now the red squares are taken, the green squares are free. How do we coordinate the behavior of these autonomous cars so that they park, but perhaps in this case also minimizing collective traveled distance, that they park safely, and safely means they avoid collisions. Of course, if 2 cars are in the same square, then a collision will happen. So here are examples of properties that you could write. And the idea is that for PRISM-games, the most recent version, you can specify these models, you can verify the safety, but you can also automatically compute these equilibria strategy, in this case, social cost Nash equilibria strategies. Now, model checking for equilibria properties is much more involved, and in fact, we kind of draw on techniques straight from game theory by matrix games and backward induction, and combine that with value iteration. We need to compute an equilibrium in every state as we iterate, and complexity is p-space. And just to show you one more, one lesson, I suppose I do not have time to explain this protocol, but this is a protocol that was introduced by Halpern and Teague with a theoretical analysis. We were able to model this protocol using the N coalitional variant of the logic and analyze it with respect to the bias. Alpha is the bias of the coin, and we confirmed automatically the theoretical analysis. And the theoretical analysis said that the rational player would cheat given a high enough probability other players would share. So if you are interested, PRISM-games has recently been released for concurrent stochastic games, and there are also quite a few case studies, not just concurrent, but also the older turn-based games, and of course for equilibria properties as well. And where am I taking this work? Well, so far I have considered models which were constructed for fixed inputs. But of course, these days with AI, what we need to consider is we also need to consider learning and inference from data, and also consider adaptation, perhaps also strategic adaptation. So for neural networks in particular, there is a variant which is called a Bayesian neural network. And for that Bayesian neural network, you can talk about a probabilistic analog of properties. But in this case, you are talking about the probability which is conditioned on the training data. And now I'm now working on extending probabilistic verification to such settings, which started with a paper at UAI this year. And okay, just to conclude, well, I've given you a very quick tour of what mainly PRISM-games can do. highlighting the Nash equilibria and strategy synthesis for Nash equilibria, which are stable strategies. But of course, there are many challenges and directions. In particular, scalability is still an issue. Partial observation has not been tackled at all. There are many more case studies that can be done, and of course the probabilistic verification for Bayesian neural networks. And I want to finish by acknowledging my funders and also collaborators in this work. So thank you.